Hey everybody, today what I'm going to do is I'm going to show you how to simplify rational expressions. Now some of this we did, I think, way back at the beginning of the school year, and a lot of this is going to involve factoring of some sort, where you kind of take out a GCF, or perhaps you do a little bit of factoring of a polynomial. So I've got quite a few examples here to go over, so let's go ahead and without much delay and just get started. All right, let's go over a few housekeeping things here before we get too deep into this. One of the things that you're going to want to do when you're doing this is the key word here is going to be factoring. Okay, you're going to want to factor the numerator as much as possible. And this is maybe a little repetitive, but factor the denominator as well as much as possible. That means pulling out a GCF. That means if it's a difference of two squares, if it's a perfect square trinomial, anything like that. If there's anything that you can possibly factor out of it, factor. And that's going to involve, of course, the factors. Okay, this first example here. Now, these are basically just two monomials. You have a monomial on the top, and you have a monomial on the bottom. And there's a couple different approaches you could take with this one. I think you're basically coming into this lesson knowing already maybe how to do this first example, but it's worth kind of just revisiting this. But one approach we could take with this is just by eyeballing, the 36 and the 60, and looking for what is the greatest common factor that goes into 36 and 60. You might be thinking, well, 6 works. Well, that's not the greatest. You can also divide by 12. So if we divide those by 12, we're going to get, 36 divided by 12 is 3, and 60 divided by 12 is 5. So you get 3 over 5. And then what you do is when you look at the exponents here, remember you have to use the quotient rule. And the quotient rule tells us that we better subtract or find the difference of the exponents with the common bases. So the x's, if you look at the x's, and we have 5 x's on the top and we have 3 x's on the bottom. If you look at the common difference there between the two, you're going to get squared. You're going to get x squared. So 2 x's remain in the numerator. And then, of course, looking at the y's here, look at the y's. There is 1 more y on the bottom. 3 minus 4 is negative 1. But really, we want to keep the y's positive. We want to keep all of our exponents positive as much as possible. And that's as far as we can go with this problem. Really, I didn't need to put that 1 there. So I could have just written 3x squared over 5y. That's an acceptable answer. Now, moving on to example 2 here. Now, this one, this is not like the first example where we had monomials. In this example, what we're going to do is we're going to look for possible, especially in the numerator, we're going to look for a possible GCF that we can pull out of 10x plus 90. And remember, I think this is going to be a lot easier doing this task if you take the greatest common factor out. So the greatest common factor of 10x and 90 is going to be 10. So you pull the 10 out, and then what remains is going to be the quotients, what you divide out. So 10x divided by 10 is x. 90 divided by 10 is going to be 9. Now the bottom, nothing really happens to that. Nothing really happens to x plus 9. What we're left with here, now I could put parentheses, I guess, around that. What we're left with here is we have, we have 2 binomials here. We have 2 binomials. We have x plus 9 on the top, and we have an x plus 9 on the bottom. And what that means is you can factor out, factor those out, like cancel them out. They cancel each other out. And what's left in all of this, what's left is just 10. So the answer is essentially just 10. That's all that remains out of this example right here. And the thing you got to remember about this, now this is not necessarily has to do with this problem, but let's say I had on the top like 10 plus or x plus 5, And on the bottom I had x minus 3, something like that. And I think I might have addressed this way back when we were talking about just simplifying polynomials in general. Some of you might think, well, I can cancel those x's. And actually that's not true. You cannot. You cannot cancel those x's one bit, because this x is attached to this 5 via addition. This x is attached to this 3 via subtraction. So the only way I could cancel out this x is that if it matches up perfectly with this binomial right here, and it doesn't. So the only thing I can cancel off with this x, that will make this x right here cancel, is another x plus 5. And this is not x plus 5. So this would be as far as you can go with this problem. You couldn't do anything else with it. So that is the solution. You know, I shouldn't call it a solution, but that is the simplest form for what we got for that particular rational expression. We got 10. All right, moving on to example 3 right here. We're going to, again, look for as much that we can factor out of the numerator and as much that we can factor out of the denominator. You know, kind of a rule of thumb here, when you're factoring in, if you notice, like, you know, maybe you factored and nothing looks like it's canceling out, perhaps you didn't use the greatest common factor. So maybe revisit what you factored and go over it again and look, maybe, are there bigger numbers? Did you take enough out? Did you do it right in the first place? So there's a lot of things that you can look for that could perhaps make this a little bit easier. Now, one thing in example 3 that I notice is that there's a negative leading coefficient. Now that may or may not mean much, but it does sometimes help to factor out. This doesn't always work out, but it sometimes helps to factor out a negative. So I'm going to factor out negative 7, because 7 is a factor of course, itself and 28. So there's no x factor that can come out of that. So you're going to be left with negative 7, and then x squared minus 4, something like that. And then look on the bottom here. We've got x squared minus 4. Now, what I was going to say was, like, this is that's a difference of 2 squares, and we could factor it, but we can factor it as is right now. We can just factor it with what we see here. Like this x squared minus 4 is exactly the same as this x squared minus 4, so those cancel each other out. So what we're left with is a lone negative 7. I mean, it's really negative 7 over 1, which is really just negative 7, right? Just write that as your solution. Now, on example 3 here, let me kind of show you what happens. Let's say we didn't factor out the negative 7. Let's say we just factored out 7. Well, if we factored out 7, see what happens here? We're left with negative x squared plus 4. You know, kind of the same thing, but not quite. Forgot the squared there, but you got x squared minus 4 here. And those are not the same thing. I can't cancel out this x squared with this x squared and this 4 with this 4, because it's not exactly the same thing. So that doesn't work. So you can see why it helps to factor out that negative, because it will make that a minus, and then it'll match up with the denominator. You know, it'll make it so that x squared minus 4s will cancel out, leaving us with what we got there. And like I said, if you end up with what seems like too much in the numerator and too much in the denominator, you might have missed a lot. So go back, revisit all the factoring, and see what you didn't do, perhaps. All right, looking at example 4 right here, if you look at the numerator, you'll notice you have a trinomial. Now, with a trinomial, you're going to have kind of a special type of factoring. There isn't a GCF that we can take out of x squared, 16x, and 64. You know, there's 16 goes into 16, and it also goes into 64, but it does not go into x squared. So there's not a common GCF to all 3 of those terms in that trinomial, but we've learned something called the product sum method. Now, if you remember about the product sum method, to kind of review here, the middle term, as long as it's all kind of in standard notation, the middle term represents your sum value. Your C term, your last term, your constant, that represents your product, meaning like that has to do with multiplication. And the thing that I taught you guys was to kind of focus on that product number and factor it out. What I mean by factor it out, I mean like look for factor pairs. You know, we've got, start with 1 and 64 and then kind of work your way up. 2 and 32. 3 is not a factor of 64. 4 is though, 4 and 16 is. 5 is not a factor. 6 is not a factor. 7, no, 8 is. 8 times 8 is a factor there. And then I ran out of factor pairs. And then what you're going to do is you're going to look over this list here. Look over your list and you're going to look for a sum that can make 16. Now remember, when I taught this, I kind of told you kind of ignore the sign for the time being. Not completely ignore it, but we're just looking for 16. So what sums will make 16? Well, is there a way to make 1 and 64 into 16 by adding or subtracting and putting a negative somewhere? No way. Is there a way to make 2 and 32 into 16? Nope. 4 and 16? No. And I know you guys are probably screaming at me or like 8 and 8. I know it. That's it. So 8 and 8. Okay, now if you remember, when we do this, what we're going to do is we're going to set up two kind of blank binomials here. And I'm going to put x here, I'm going to put x there. And we've decided here that 8 and 8 make the product of 64, because 8 times 8 is 64. But we also want to make sure that 8 and 8 make the sum of negative 16. Well, if we put plus here, well, that makes positive 16, so that's not going to work. If I do plus and minus, well, that's going to make those cancel each other out, and it's going to give us nothing. So that's not going to work either. So what we have to do is we have to make a minus minus, because a negative and a negative, if you think about that, that works. Negative 8 times negative 8, that equals the product of 64, which is positive 64, and negative 8 plus negative 8 equals negative 16. So the product sum all checks out on that one. All right, on the next, in the denominator here, you might notice something that's called a what? That's called a difference of two squares. Now, difference of two squares is factored like this. You're going to factor like that, where you've got, you know, x and x here, and then what's the square root of 64? Well, 64, the square root of 64 is 8. And now the way difference of two squares work is always going to be plus minus or minus plus. It doesn't really matter the order in which you do it, but one of your binomials has got to be a plus, the other one's got to be minus, or vice versa. And then if you look at this, we're going to look for things that cancel out. So like this negative, this 8 minus, this x minus 8 right there will cancel out with this x minus 8 right there. And then this is where this is what I was talking about earlier, and it's very tempting. But let's look at what we're left with here. We've got x minus 8 on the top in the numerator, and we've got x plus 8 in the denominator. And it's really super tempting to try to cancel out those x's right there, but they cannot. They cannot cancel out one bit. The only way this x can cancel out is if it was matching up with this x minus 8 down here, and it doesn't. Now, I know there's an 8 here and there's an 8 here, but it's attached, you know, if it's attached via addition or subtraction, there's only so many things we can do with it. And the only way we can get rid of x minus 8 is if there is an identical, you know, an exact match of x minus 8 in the denominator. And that is not true here. That's not happening. So that's it. You know, we really can't do anything else with this other than just leave it as is. And I know that doesn't look like an answer, but it is. You know, well, in terms of what we're doing for our purposes, we're trying to simplify it down into, you know, simplest rational form. We've done that, right? As you can see, these examples are getting, you know, increasingly a little bit more challenging. You know, there's a little bit more factoring going on in each one. So for example, 5 here, right here, we're going to look at that product sum method. We're going to look at the product sum, and remember, focus in on that 40. 40 is our product, and I'm going to factor out 40. So we got 1 and 40. So these are called factor pairs. These are not prime factors. These are just factor pairs in general. So if you got 2 and 20 makes 40 when you multiply them. 3 does not work. 4 times 10 makes 40. 5 times 8 makes 40. 6 does not. 7 does not. 8 does, but we already have that written down, so don't write it again. And this time around, we're looking for a sum pair. We're looking for a sum pair that is going to make 3. I know it says 3n there, but we're looking for 3, most importantly. So the sum pair that sticks out at me is the 5 and the 8. All right, so let's put this all down here. So 5 and 8 will make positive 3. Now we want to make positive 3. So if we want to make positive 3, we want to make sure the positives win out and the negatives don't. And everything checks out there. Remember, if I look at the products, does negative 5 times positive 8, does it equal negative 40? That checks out perfectly. And does our sum match as well? Does negative 5 plus 8 equal positive 3? And that checks off too. Because those, you want both of those to check off simultaneously. It can't be just like, well, one of them does, and that's okay. It's got to be both. It has to be both. It must be both the product and the sum. All right, so we've completely factored the top. Now we're going to look at the bottom. And there's a little bit more going on in this bottom one than on the top. And one thing that sticks out at me is that there's a GCF that we can pull out of this. I notice there's an n term in every single one of those terms in that trinomial. So we can pull out an n. So I'm going to do that first. I'm not going to try to do too much at once, but when I take out the n, I've got n squared plus 9n plus 8. We've got that. And then right there, we've got a trinomial that could perhaps be factored into, using the product sum method. So I'm going to write the numerator the way it was. I'm going to write this the way it is. And now I'm going to look at the product sum method, but this time I'm just going to look at the number 8. 8 does not have a ton of factors at all, so that's going to be pretty easy to factor. That's got 1 and 8, 2 and 4, and we're through. Okay, hopefully that wasn't too hard. And we're looking for factor pairs that are going to make a sum of 9. That has got to be it. So I'm going to put n, I'm going to put n here, and I'm going to put 1 and 9 here, or 1 and 8 I mean. Put 1 and 8, and I want to make sure that that will make positive 9. Well, in order to make positive 9, they both have to be positive. And does 1 times 8 make positive 8? It sure does. So now we're all set. We've completely factored the numerator. We've completely factored the denominator. And now we're ready to start canceling stuff out. Right? Sometimes I think when people do these, the biggest mistake people make is that they start canceling stuff way too early. And I'll talk about some of the more common mistakes a little bit after this, but let me show you what I mean. Like this right here, like this n plus 8 can cancel out with this n plus 8, and that is it. That is all you can factor out. So in the numerator, what's left is n minus 5. Now you can keep that in parentheses if you want to, but you don't have to. You could, you don't have to. And then in the denominator, we've got n times n plus 1. But nothing cancels. This n and this n cannot cancel out. That's it. We are through with this problem. I know it seems like, well, there's got to be more that could cancel out, but there isn't. And let me go back to the original problem. Let me just kind of show you what I mean. Let me just write it exactly the way it was written down before. And this is a big mistake, so listen carefully. This is, I think, especially newbie algebra students, they'll make this mistake quite commonly, and they'll start thinking like, oh, I can cancel out n squared and n3, like using the quotient rule. No, you cannot do that. Or they'll think, oh, I can make 3 into 1, and I can make this 9 into 3, and I can make this, I could divide 8 and 40 by 8, so this turns into a 5, and this turns to a 1. And that is completely, entirely wrong. That's going to be a mess of a problem. That is never, ever going to work. You got to, in order to cancel stuff out, you've got to get everything completely factored. Then start looking for what can cancel out. Like binomials can cancel out with other like binomials. Now this n right here, like I said, I keep repeating myself, but it's super important because these are mistakes I've seen year after year after year. And those, like those n's right there, some people think, oh yeah, those can cancel. They do not. This n does not cancel with that n either. So we're through with that problem entirely. All right, now getting to the last problem here, the last example that I have, we're going to look for perhaps a GCF in the numerator, and a GCF that jumps out at me is got to be 3. So that turns into n minus 5. And then in the denominator, that's a trinomial. So perhaps, and we're not guaranteed, you know, sometimes, you know, the thing is, I've told you, like, if sometimes things won't factor, but a lot of times, there's going to be a few times where like nothing factors, nothing cancels out, and it is what it is. Just make sure you do your due diligence and check everything out. So you got 10 here. So 10 is going to be, when I factor 10, it's going to be 1 and 10, 2 and 5. And that is all you can factor for 10 in terms of factor pairs. And we want factor pairs that will make 7. And it's got to be 2 and 5. It has to be. So I'm going to put n here. I'm going to put 2 here. I'm going to put n here and 5 here. Now remember, it does not matter whether we put 2 here and 5 there. We can completely turn this around, put a 5 here and a 2 there. It doesn't matter. What matters, however, are the signs. We want 5 and 2 to be negative 7. So in order to make negative 7, we've got to do negative 5 and negative 2. And does that check off as a product? Does negative 5 times negative 2 equal positive 10? It sure does. So there's your product and your sum, both working out. Now notice we have everything factored in the numerator. Everything's been completely factored in the denominator. And now we're going to start looking for stuff that can cancel out. In this case, right here, this n minus 5 will cancel off with that n minus 5. And what's left is a 3, just a single 3, a lone 3 in the numerator. And in the denominator, n minus 2, a binomial. And that's it. Now, just while I'm thinking of it, because I know this is probably going to happen on your IXL, or maybe it doesn't, because I don't do all the IXL problems myself. I sometimes just look at them and go, oh, this is what we're learning, but sometimes they throw a problem that I didn't necessarily do an example for. So let me show you what I mean. Let's say this is totally a different problem. Completely, this has nothing to do with number 6 or example 6 here. But let's say we have, we've gone through the process of canceling stuff out. Let's say we have like n plus 2 and then n minus 3. And in the denominator we have a 6, and then we have an n minus 3, and we have an n plus 2. Let's say we factored it like that. Okay, and I just want to kind of make a point. Like I said, this has nothing to do with the problem we just did. But just while I'm thinking of it, I want to just kind of show you what's going on here. Now notice the n plus 2 and the n minus 3 are not in the same order. Does that matter? No, it doesn't matter. So this n plus 2 can cancel with this n plus 2. This n minus 3 can cancel with that n minus 3. And here's the point I'm trying to make about this example here that I just kind of did off the top of my head, was that everything in the numerator here canceled. But that doesn't mean there's a 0 here. I think some people think, oh, there's nothing left, or I'm going to put a 0 there. No, there's something left, and we've talked about this too in algebra quite a bit. There's a 1. Remember, there's invisible 1s everywhere in algebra, especially. So we have to put a 1 there. We can't just say, well, it's empty. We have to put something there in its place, and there's still a 1 there. And then the 6 was all that was left in the denominator. So you got 1, 6. And so that is it. So you got 1, 6. If you put 6 down as an answer, that's not the same thing. 6 is not equal to 1, 6. Those are not equivalent statements. You know that. All right. So that would be a false statement right there. So 1, 6 has got to be it. And the point I was trying to make about this one was showing you that, when you have, sometimes everything cancels out, completely. Everything cancels out. But that doesn't mean nothing's left. There's still something there. There's still a 1 there. Okay? So always kind of keep that in mind. I mean, if there was a 1, here's the thing. If there was a 1, let's say the 1 was left in the denominator. Do you need to show that? No, you don't have to. I mean, you can get rid of it. I don't think it's wrong either to write 6 over 1, but at this point, I guess that would be kind of considered superfluous, which is, it's just unnecessary. You don't need it. So you can just write 6. But in this case, you definitely need that 1. It's necessary. It makes a difference. There's a big difference between 6 and 1/6 for sure. Okay, so that was your crash course on simplifying rational expressions. We're probably going to spend like another day on this just because I know that it's tricky. Try to get through this. Let me know too, of course, if you guys have any questions about anything. And please let me know if I made a mistake somewhere in the lesson as well, because I think I went through this kind of quickly. And I know I talk fast and I go through stuff, or sometimes I talk slow, but I know that I'm not perfect at anything. So you could, if I made a mistake, just let me know. I'm okay with that. My feelings are never hurt by that. So, all right, everybody, I hope everyone's doing okay. And hey, we're in May. We're in the final weeks here, and hopefully everyone's getting through okay. This is crazy e-learning time, and I know it's tough not to be at school, not to be around each other. So please let me know, though, if you need anything. All right, so everyone have a great day. Take care.